Now we should be streaming.
Yeah, that looks better.
Yeah, are we on?
Yeah, seems so.
Where is my channel?
Yeah. Well.
Yep, we're streaming. Yay! It works. So we'll start at 5 sharp. I think people are coming in still. So what we usually do is we take questions right at the end. So after your talk, if you want to ask questions in the middle, it's up to you, but I usually recommend doing this after.
Oh, no, we can do it at the end. I think that's...
Yeah, so I'll briefly introduce you to anyone who doesn't know you already. And then you're good to go.
We have 2 more minutes.
We have 2 more minutes. If you want to say something cool for 2 minutes before the whole world.
No pressure. Say something cool.
That was the moral of it.
You know, this is also live on YouTube, so I rather think long about it before I say something.
So for people who don't know, we are live streaming this on YouTube right now.
You can access the link also from the gallery view in Zoom. Up there it says live, and on YouTube, if you click on it, you can copy this or you can open it directly. So
we are trying to make this more public.
Did someone already posted on Twitter that it's live?
No, this is just a trial, so I didn't want to publicize it too much.
Okay, I can do that, but Bene, are you fine with posting the link live?
I mean, it's going to be on YouTube anyway, so
okay,
yes, of course.
Then I do that. Or Ashima, do you want to do it?
I'll do it.
Okay.
Hi, Alex.
hi, Alex.
Hello from Montreal.
Is it early or late?
It's 11 a.m.
That's good.
It looks like night already, though, for some reason.
Well, it's cloudy, and snowy.
Okay, so the tweet is out. Okay, so welcome everyone. I am delighted to have with us Benedikt Ehinger for the colloquium today. He is a born and bred Coxie, so if you don't already know him, he did his bachelor's, master's, and doctoral studies at the University of Osnabrück Institute of Cognitive Science. He's been a mentor to a lot of us PhD students who are already here. Bena is now a tenure track professor at the University of Stuttgart, and let's give him a warm welcome. And yes, Bena, please.
Thanks. Yeah, I prepared a little bit here, something that I want to share. You should see my slides now. And a small animation. Awesome. Perfect. Okay, cool. Yeah, thanks a lot. It's great to be back virtually and talk about this. And yeah, for some of you, this will be more like an update because actually this kind of work started in Osnabrück. Yeah, back when I was a PhD student with Peter. And it's a great ongoing collaboration. Well, not this one, with Olaf. This is funny. Wait, sorry. Okay, there's a great collaboration with Olaf Diemigen from Berlin. And today I'm going to talk about what I, in my short time that I had to think of a title called Next Level EEG Analysis. I don't know if it's next level, but at least it allows to do new, to analyze new EEG experiments. So maybe we reach the next level, I don't know. Okay, so I want to start out with the question of why we would like to. I teased this in the abstract a little bit. Like, do you want to read a book, like understand EEG while reading a book or while walking around or so? And then the first question, of course, is why do we even want to do this kind of naturalistic experiments, especially with the combination of EEG eye tracking? And I like what I'm doing most of my stuff currently, like all my methods work or so. Yes, because I think if we are limited by the tools or the analysis methods, then we have to improve somehow the analysis method, and then we can also do new experiments. We can ask new questions about the brain, and then I'm especially attracted to not only looking at EEG, but also looking at eye movements, because well, you get a lot of data for free in some sense. So you're constantly moving your eyes, right? So this is 4 times a second, and maybe you can use this high data rate. Then also, there's the argument of ecological validity. So because, well, whenever you do something, you typically move your eyes, but if you're in a laboratory, you typically don't move your eyes. And I at least assume that most of visual cortex is wired up so that it can accommodate eye movements, or it has to accommodate eye movements. Yeah, so that's my last point. The brain evolved around eye movements. So I put a bunch of icons down here, and I think all of those studies or topics or whatever you want to call it, like VR, reading, mobile EEG, infants or so, they all either have eye movements or they will, in some other sense, like the multimodal one, benefit of the methods that I'm going to discuss in this talk today. Okay, but let's start. So this was just maybe an outlook of why you should be interested in what methods work I'm presenting here. But let's start out in some sense simple. With what do I mean with statistical modeling of combined EEG eye tracking experiments? What is this method all about? Okay, so let's take a classical EEG experiment. This is very simple. You fixate in the middle. You're sitting in some kind of chamber. You fixate in the middle at a small fixation cross, and at random points in time, I flash you a house here, or I flash you a face, and I'm interested in what is the brain activity or the difference between brain activities regarding the house or the face. Right, then I record the EEG. This is typically, we are recording voltage differences. They are very small, so this is hundreds of microvolt scale, and these are all the different channels. So you have put these electrodes all around your head. Look, something similar like that. I don't see any house or face activity in there, and that's because typically we have to repeat this for 100 times so that we can average over it. Okay, so we know when in time the house starts and when in time the phase events start, right? So then we can cut out the data and average it, and maybe just select a view of those channels where we already know that we're going to find something, and then we get what we call an event-related potential. So this is like the average over hundreds of trials. So I would just explain it once for those who never seen this. This would be the time. So 0 would be the onset of the stimulus. Because we have perfect control of that, we know exactly when the information hits the eye and then when the brain cascade works. And this is the so-called ERP in microvolts. So it's very, very small potentials that we are actually measuring. So now I will jump directly to eye movements. And eye movements are these rapid, they're called saccadic eye movements because they are rapid movements looking all around the monitor here, and they are super helpful because we don't see anything or we don't see much information in the periphery as visualized in this simple sketch here, but we only see really sharp in the middle where we are fixating. So we move this around. Now we can play the same game. We measure these eye movements. We measure also EEG at the same time. And now we put in the eye movements. And already you can see, maybe appreciate here, we have many more of these events here because eye movements are so fast. They happen every 250 milliseconds or so. plus minus. Now we can do the same thing again. We can cut towards these eye movements, and we can build these kind of ERPs. Now, completely different channel, different experiment. And so it's just an example how this looks like. It would typically look a little bit different, but maybe more to that. I have an example later going on. Okay. So when you do this, then there are typically, or Olaf wrote a paper about the 4 problems of co-registering or combining these 2 modalities, EEG and eye tracking. And 2 of them here, would be the data integration. So how do we align the streams? And then this one here, I think this one is completely solved. There's not much to do anymore here. I think we now have a pretty good ideas and multiple ways to do that. The second one here is also not something I'm going to talk about today. This is whenever you move your eyes, your eye acts as an electrical, in some sense, a dipole, a battery. So whenever you shift it, the whole EEG will be influenced because of this shift of eye movements. And this is because of the muscle artifacts and of course how the eye is built up, right? So this is very uninteresting because it's not brain activity. Well, uninteresting for me right now. But there are super cool methods that were actually developed in Osnabrück to correct for this. And so I also think this is pretty much solved. So these 2 I would just ignore. These 2 here, yeah, this one are like turned out, took a little bit more work to still do. And the one is what we call overlap, and the other one nonlinear covariates. And I will discuss this in much more details in the next slide. I just want to highlight that there was a toolbox here, the EEG toolbox, to solve these 2 problems, and we wrote a new toolbox, the Unfold toolbox, that tries to address these 2 problems. And there are also papers to it. And yay, today a new paper got accepted that actually talks exactly about eye movements and EEG analysis. So check it out. It's in Journal of Vision. It's open access. Okay, so let's start with this problem here. Discuss the problem first. Then we discuss the other problem, why it's a problem, and then we discuss how we are addressing it. Okay, so let's have a typical EEG eye tracking experiment. We measure EEG, we measure eye tracking. Subject is looking around on the screen, looks at cars, looks at faces, and we are measuring, or we're visualizing one channel here, right? So this is what we typically get. And we know when the subject looked at a face and when it looked at a car. What we actually would love to have or to measure is what we could assume is underlying. Whenever we make an eye movements, our cortex gets super excited. Oh, some new input, let's analyze it. And it gets some response. And as you can see here already, it's not even finished analyzing this response, then the next eye movement comes already, and the next input comes, right? So in some sense, cortex is doing many things, multiple things at the same time, or we can at least assume that it does. So somehow it would be nice, or you could argue it would be nice to not look at this, but look at that. And I would even make a stronger point. I think it's really important to look at this and not at this. Because let's say you're just cutting the data to this onset of the eye movements, right? Whenever you make an eye movements, you put these events, you cut them, you average them. You do it for the one condition, for cars and for faces. And then you look at this and you say, oh, that's perfect. I have so many differences. This is really cool. I can write maybe one paper for each of the difference, or look at all of these things. And I will show you in a second why this might be problematic. Okay, I mentioned on the previous slide that these events are overlapping, right? So the eye movement is maybe every 200 milliseconds, but maybe the brain response takes 300, 400 milliseconds. And what I did here is I wrote a simulation where I take this black shape and I change how much overlap there's in time. And so I simulate 1,000 events, and then I take the ERP. And this is the orange line. So if I increase the average overlap between these events, then I approximate the black curve. So when the mean overlap is all around here, I have the black shape, so there's no problem at all. But if I increase the overlap, then I get arrows here, or like deviations here and deviations here, and the whole shape starts to break down. Now you can say, okay, yeah, so what? It's not a big deal, but it's a problem as soon as you're basically sampling the orange curve at 2 different mean overlaps. And what I'm meaning with this is, let's assume we are looking longer at cars than at faces because we have seen so many faces, but not so many cars maybe. So we we are basically sampling the orange curve when this bar here is at 300 milliseconds for the cars, but at 200 milliseconds for the faces. And that looks like something like this. And then you see that they are starting to evolve differences in conditions, depending on the simulation parameter before or after, that are completely just because we are basically sampling this curve at different durations of our event. So yeah, this was the first problem. And the second problem is kind of related to this. I will discuss it at the very end of the talk, but this pertains to the linear covariates. And what do I mean with this? It's very well known since the 70s that if you make a large eye movement, that this first response here, which is called the lambda response or the P1, also sometimes some debate there, is larger, much larger if you make a large eye movement than if you make small eye movements. Okay, and now we can play the same game again. What happens if we have a difference in saccade amplitudes? Maybe because we like the cars so much, we make longer eye movements towards them. Then typically we will also sample this curve here. Let's say this is maybe 3, this is maybe 2 degrees or so. We are sampling the curve at 2 different points. And so we will see a difference here, right? And that this difference, again, it's real in the data, but in some sense it's also non-real. You would like to look at this effect while having the same mean saccade amplitude. You don't want to necessarily look at all the effects that are due to this confound. I think you get it. Okay, so let's have an overlook. We had all these effects here. Now I use the magic of the unfold toolbox, and I model the overlap somehow. I will discuss this in a second. And I will apply the unfold toolbox again, and I will also model the covariates. And as you can see then, from this data here, I can recover what I termed the true effect, what I simulated into the data. So at least in this simulation, and this is an actual simulation, actual application of the toolbox, but without any noise, so it's easy in some sense. Yeah, we can address this problem, so that seems to be cool. Okay, let's say you're a researcher who doesn't actually care about eye movements, and then I still have some ideas for you why you should still care about this overlap and this non-linear confounds. For instance, here, let's say we take this experiment with the house and the face again, and whenever you see a house, you press the one button and the face the other button, right? Then you again have overlapping responses. Now, not of the face and the house, because you can just move them away, but of the button press in the house or the button press in the face, right? And let's imagine maybe reaction time is different between the two conditions. So then the button response will be closer to the house response, closer to the face response than to the house response. So again, then basically, in some sense, this overlap is again biased. And let's also say you didn't control for something that affects the P1, which is the contrast or the luminance in these conditions. So you have a difference, a systematic difference between the two distribution. And then again, you should you sample this luminance effect at different mean luminances, and you might run into problems. This is how I set up the simulation here. So you have this luminance effect, you have a true effect again, and you have two events here in this case. And yeah, we apply unfold toolbox again. You have lots of biases here in some sense. You can remove the biases and you can remove the covariance effect. So it's the same story, basically, that we use, that we were just interested in correcting these eye movements, and then we found, hey, wait a moment, this is a problem that goes through a lot of, or it's a potential problem that goes into a lot of effects. A lot of other paradigms, sorry. Okay, so how do we actually model this overlap between these adjacent event responses? And I hope the problems got clear, because for me, it's more important that you get the problems than you get the actual solutions. Maybe the solutions are also a little bit specific. But let's first start with what's called the mass univariate linear model. And this is basically a way that you can introduce traditional ERP analysis that are often like you calculate the average in one condition, other condition, and you subtract them. This is just a generalization of that using the linear model or linear regression framework. So let's say you have here n epochs or n trials or n events, and you cut the data to that. So time 1 is when the event happened, and then this is what the brain response look afterwards. Now we are selecting just a single point, and we are putting this into a linear model. So linear model for people who like math looks something like this. This is going to be a little bit hard to follow for people who have never seen that, but I will try my best. This is called a design matrix. It basically specifies what each of these epochs belong to. So the first epoch belongs to this one condition, and the second epoch belongs to a condition that has an additional effect. So we have a second column here, right? We solve this for this unknown parameters, and we are more or less throwing away the error, or we're trying to minimize the error. So with these two values, we try to approximate what we are seeing here as best as we can. Then we repeat this. So we take this, we shift it to the next time point, we repeat it to the next time point. And basically what we get out is two curves, these two factors here for each time point. And that would, for instance, in this case, how we set up the design matrix would be the response of cars. And this one would be the difference of cars and faces, but it's just a matter of how you set it up. Just a quick note because I'm trying to connect lots of views. Again, if you don't understand all of this, it's totally fine, but maybe you will understand this. Generating this by hand is a little bit tiresome. So people thought of a really nice syntax to it. This is called the Wilkinson notation. And I'm bringing this up here because it's very, very much used in cognitive neuroscience or cognitive psychology. Also, whenever you start up R or so, also in MATLAB and Python, it's very popular because it can describe models so nicely. And basically, you have a left side, this is what you want to explain, and this is the right side, what you want to explain it with. And in the Unfold Toolbox, this is the way you'd specify a model, and it's neat because it's if you give me this kind of formula, I know exactly what your model looks like. I know 90% of what the model looks like. That's cool. Okay. So in order to understand how we can now do the overlap correction, let's have a look back at this initial sketch that we had, and let's try to understand what kind of information we have in here that could potentially allow us to like disentangle these, do the deconvolution. And let's think about this. We basically want to know if I have a phase event, let's say 150 milliseconds afterward, what would be this value here if I have a phase event, or on average, right? But this is the only thing that I recorded. I would like to know this one, but this is what we recorded. I can think, okay, hey, this is actually the sum of this actual response here, plus a response of an event that is much longer time ago, right? Because electrical potentials in the brain add linearly. This is, at least in some sense, a useful assumption, right? And now, okay, this doesn't help me because now 1 point is explained by 2 points. I can, if I don't know where these points are, I can arbitrarily shift them around. But I have the same point here at the later event again, right? Now it has a slightly different value to that point here. And importantly, it has a different markup, right? And now it consists of, let's say, the responses of the potential responses of 3 events. Because I have hundreds of events, I will have, for each delay here, I will have hundreds of different constellations. If I now assume that all the blue responses are actually the same, or at least can be modeled in one with one design matrix, I can assume some events are similar. Then I can try to reverse it, and I can try to estimate these things. How it looks like in practice is now a little bit more complex. Basically, I'm now not. I built a linear model again here. You can see this. This is the typical linear model formula, but now I'm not trying to explain single tridata, but continuous EEG recordings. Yeah, okay, so I have all the EEG samples here, and now I think back on the previous slide, every sample that I had here on the black curve consisted of multiple responses to events with different delays. And I can put these delays here, what I sometimes call time after event, or tau. So I have one event that was immediately, this is the orange one here, so I put a 1 here. I have no event in the previous sample, I have no event in the sample back, and I have an orange event here 5 samples ago, so I put a 1 here. Again, because this EEG signal here consists of that response here plus that response here. And in addition, I had another event here 4 samples ago, so for the condition B, I put a 1 in here. And I call this a time expansion. If I now look at this at the second step here, everything is just shifts 1 down because now the condition A event is 2 samples ago, or like one sample, two sample, one sample back. And this one also, this one dropped out of my analysis window. This is of course a toy example. We're just modeling 5 time points. But anyway, if I solve this for these betas now, then I would again get the same curves. Oh, sorry, I should probably fill in the whole design matrix. You get this kind of staircase patterns. If you're an fMRI person, but not many in Osnabrück are, but if you are one, then you know this under FIR deconvolution. It's one of the essential tools to analyze fMRI data. Okay, so now what changed? You have not many linear models, each one for one time point, but you have one big time model. If I would fill in realistic data, I would have some 2 million rows here, and I would have maybe 1,000 columns, because each millisecond that I'm modeling gives you one predictor, right? So the models are, yeah, they're pretty large now, 1,000 predictors and the likes, and you need some special tricks, but the Unfold Toolbox takes care of that. Okay. Yeah, if you didn't follow through all of that, don't worry. This is, yeah, it needs time to sink in, I think. It's hard to do in a single talk. Okay, I want to show you, but I want to show you an application, and I want to show you something where it worked so well that we are, yeah, that's why when we came up with this magic, actually Peter came up with this magic wand, because it works so well. So this is work with Annalisa Gerd, who works in Peter Koenig's neurobiopsychology group. And she's interested in looking in when people are looking at images, so they do eye movements and EEG, when they look at faces versus other things. So quite close to the examples. So we had here, we had an ERP to faces, we have ERP to other objects. And as you can see, we have big differences here. We have differences here. We have even differences before zero, very exciting in the beginning. Maybe there's something going on before zero, like peripheral preview and the like. But you can also see we didn't apply Unfold here yet. I want this animation goes all wrong. But if we apply Unfold, then we see that most of these effects are gone, and only the effect that we would expect from the literature, from classical experiments, actually remains. And that's super cool. I will go a little bit more into the data here. It turns out that there was a big overlap problem that explains this one here. And that was when you turn on the stimulus, people will, first of all, scan for all the faces. So you will have a lot of overlap in face stimuli with this, in face fixations with the stimulus previously. They are all very close to the stimulus. And the other, exploring the rest of the image, comes much later, where there's no influence of the stimulus. So if we additionally model the stimulus overlap here, we get rid of it, well, nothing in before zero. And then the bits here, this would be the subsequent fixations. Okay. Sorry, I have to check. Okay. Yeah, I want to make this as broad as possible. So this is in some sense an X course. And I want to say that we are not restricted to things that are events, like an eye movement, I can define as an event. Now, like suddenly something is coming in, or I put a stimulus on, it's an event. But sometimes I have things like music in or speech or something like that, where it's much harder to define what is really an event, maybe a word onset or so. But maybe in music, it's even more difficult or so. So what I can also do is I can include continuous predictors. So that means, for instance, let's say I get somebody, record the EEG, he listens to speech. I can extract some kind of Fourier transform, like changing over time. How much power do I have at different frequencies? I extract one frequency band because I think this is important for my experiment or something like this. So it looks something like this. This is the instantaneous power over time of speech. And now this predictor here is for each of the samples of the EEG. It's not longer any single events that has some kind of predictor attached to it, but this is now really going over the whole EEG. Could also be like, let's say you have a moving object on the screen or so. This is the velocity or the position of the object or so. And now I can do the same game that I had before. I have the continuous EEG also for, let's say, one channel. I can now fill in, instead of having zeros and some small ones somewhere, I can fill in exactly the power of this, like the values of the speech envelope. Then I delay the whole thing by one, and I fill in the same thing. You can see that this is all on the diagonal, it's always the same value. So I'm time shifting basically this whole continuous thing that has 2 million rows again, as long as the EEG, right? And I can do the same tricks that I did before. Now I need a little bit of regularization because it's so correlated, these columns, but it's technical detail. I can do the same trick, and now I get basically out a response of how the brain reacts if I change this kind of speech frequency, if I change the power, increase the power or so. What would the brain do? What would the brain respond? And this has been TRs are super popular in auditory research and in language, because then you can basically take your language features and just find out how the brain reacts if I change the vowel onsets, make it a little bit higher pitched or lower pitched or so. And I can look at all kinds of cool things. A lot of work going on. And what I also think is cool, well, I think, you can add motion, eye movements, pupil dilations. You could think of many things that are on a continuous value. And you can also mix them. So you could have some continuous features and some event-related features. It's because you're all in this nice framework of linear model or regression analysis, or however you want to call it. Okay. Okay. This was how we are controlling overlap. And then I also discussed or mentioned that we also want to control this covariates. So how can we do that? And luckily for us, this is in some sense conceptually much easier than the overlap bit, because now we are already in the linear framework. Okay, let's have a look at the problem first. Let's say if you're in the linear regression framework, let's look at a little bit different visualization of it. Let's say we have a predictor value here, let's say saccade amplitude. And here we only plot the potential of each trial at 100 milliseconds, so at the P100, right? And then maybe it looks something like this. So we see that we have a logarithmical dependence. But if we would include now saccade amplitude as a simple effect in a linear regression, then you know from high school math that you're fitting a line in there, right? A line has a certain slope, and the slope can change. This would be the parameter of our saccade amplitude effect. And that doesn't fit, right? I mean, we have overfit here, so higher value than we should fit, and here it's bad, and here it's bad. We would like to loosen this up a little bit. One way that you can do this, and that is also sometimes seen in the literature, is basically you're categorizing your continuous predictor. So you say, hey, let's just, if this is maybe nonlinear, then let's fit one effect for 0 degrees to 2 degrees, one effect for 2 degrees to 4 degrees, one effect from 4 to 5, etc. Right? And in some sense, you can think of this as basis function, right? This is basically you're introducing a new predictor that is 0 everywhere, except when the saccade is in this bin, and then you just put a 1 in your design matrix, right? And then it's 0 again. So this is like this rectangular step function, basis function. If you now evaluate, if you fit it and evaluate it, you get something like this, which already approximates the nonlinearity here quite nicely, but it has this weird steps, right? I mean, which biological function is really this step-like? I don't think that really exists. So people in some sense just said, okay, maybe we should just add that this function should be smooth. Could be an idea. So they're changing out this basis function here in a way that you have overlap between the neighboring bins. And voila, if you do this is a special function, lots of math and things I won't go into detail here. But now each point that you're modeling here is actually overlapping with neighboring points. And if you do this, then it turns out that you can approximate this function quite nicely. So we're moving away from linear effects, and we have in some sense nonlinear effects. Yeah. An example of this is that we also present in, see, when I first made the slide, it was 2019, but now it's 2021. That's how long it sometimes takes. This is the new paper. You can read it up there. We have again a free viewing experiment here, and we have saccades that are long and small, and we are looking at the saccade amplitude effect. And turns out that if we fit it non-linearly, then so we use the spline fit that I described in the previous slide, then we can find nonlinear effects, for instance, here, where a small jump here of 5 degrees here or less than 5 degrees. Makes a big difference if you jump from 0 to 5, but much smaller difference from 5 to 10, or no difference from 10 to 15. And if you look at it differently, then you can clearly appreciate this logarithmical functions that we had here had before. Yeah. Okay. Yeah. So I want to give you one application, and that's maybe you already heard of this before, because this is actually work in the neurobiopsychology group from Annalisa Gerd. I briefly mentioned it before. This is together work with Celia Tim, Peter Koenig, and Tim Kietzmann, who's now a professor at the Donners Institute in Nijmegen. And the idea of this experiment is to go from typical lab experiments to less typical lab experiments where you can actually allow to move your eyes. That's already pretty cool. To real experiments outside in the world where you walk around. We are not there yet. Currently looking at it, but yeah. So first discuss this. It's difficult enough. Yeah. So this is what Anna found. If I show you faces, if I show you other objects in the lab, you get this kind of brain response. If I show you an image with faces and non-faces, you get this kind of EEG response. And yeah, the cool bit is we see some kind of differences at, this is an old graphic, sorry, but okay. We see some kind of differences here that are at similar points. This is run through the Unfold toolbox. Here it didn't do much because experimentally we could control that there was no overlap with other potentials. And here, as you saw before, this made a lot of differences. And then we can do this for each subject, and we can see whether there's a correlation between the difference between these conditions here, where we would expect it. And the correlation is very high. It's 0.8. This is a robust correlation. So that's super nice. And you can also, using this framework, you're not restricted to only look at these time points, which many people are still doing. They're a priori defining, I'm going to look at 180 milliseconds and only at these electrodes. But we can look at all the electrodes here. So for instance, here are all 128 electrodes overlaid. And you can see here marked, this would be significant or things that are compatible with significant effects. We can also look at this in a more topographical way. And so I'm just showing a little bit that you get a feeling of what kind of data you get. And then you're not restricted anymore to look at just single time points or single channels, but you can really, these effects can describe your whole data set, or can describe all time points, all electrodes. Another effect that is very neat, that we would probably not have found if you just looked at one time point or not one and one set of channels, is this effect here. So I said that they were looking at faces and they were looking at houses. Sorry, they were looking at faces or other objects, other fixations. And now we are sorting the triads, or we're modeling the effect of whether in the fixation previous to the current fixation, they were looking at a face or non-face. And it turns out that depending on what you looked at previously in the current fixation, it's still influenced by what you saw previously here. And this also actually starts even before the onset of the eye movement, right? So there's, in some sense, there's some lingering processing in the brain, which I thought is pretty cool. It speaks for sequential effects, and also maybe it speaks for that whenever you do an eye movement or whenever you perturb the brain again, it might rerun the calculations what you saw previously, or at least some derivative of it. Okay, and yeah, lastly, this is my last chapter. I rushed through the previous one a little bit because I wanted to get to this, because that's the thing that I'm currently working on. This is work together with René Skoukis. He's a PhD student now of mine, and his unofficial task is to try to find out when the Unfold toolbox stop working. So in what situations can we apply it, and other situations when should we not apply it, because it hurts more than it helps. And during these kind of thoughts, we looked at varying event durations. So what do I mean with this? Let's go back to the sketch that we had here. So there was this this idea that sometimes we are reacting faster, and then this button press is closer to the event here, and sometimes we're slower, and then the event is maybe further away. right? But if you think of what the brain, what this response here in the beginning does, why would we assume that the response, if I was able to categorize something fast, is identical to when we can categorize something slow, right? If I need 500 milliseconds to do something, probably it was hard or I was distracted or something, than if I could answer it already in 200 milliseconds. And this is, yeah. So in some sense, the event duration until you, from stimulus onset until you could actually do your response differs. And it's a similar story that we had before. And unfortunately also differs between conditions. In this case, it was not houses and faces, but you had to search for a target you were always present. I will go into this in a second, sorry. Okay, so I set up we set up a simple simulation. We took this kind of event, and now we changed the duration of the event. So you can see some of these events are longer, the yellow ones are longer, and the blue ones are shorter. And we put them here into this EEG, and then later we sum them up. So we have an event that's pretty long. And now always we made the overlap dependent on actually the shape, on the length of the duration. So let's say after this process reach 80% of its time, we are allowed to put on the new event, right? So if we have a short, if we were very quick, then also the next event will also come very quick. This is a simplification of what we had before, because now we reduce it to one event. Okay, and we do this for the whole EEG data set. And of course, this is what we would analyze. We wouldn't analyze this. It doesn't look too much like EEG, but it's just a simulation study. I have a real example later. Okay, let's have a look at it. So what we do is, we have here on the left corner, we have what we simulated, and this means we didn't simulate any overlap, so we moved them away very far. On the right side is whether we analyzed them using the overlap or not. This is what we simulated. And then here, I'm adding a linear effect of this event duration. This is something that people started to do right now. And here I'm adding a nonlinear effect of duration. And if I add the linear effect, then you can see this is what the output is. This is what the model thinks it would look like. It doesn't fit it at all, right? I mean, this is a really bad approximation of this, I would say. If you add the splines, then it looks much better. So already here, we can probably say, well, linear is probably not going to do it. And that's in the easy case in some sense, where there's no overlap at all. Let's look at the more difficult case. We now introduce overlap between these responses. So this is now exactly the simulation I showed previously. If we have it linearly, well, okay, it looks even worse, I guess. If we have it nonlinearly, maybe it looks even worse. And this is because we're not taking any overlap into account. So this is really just trying to somehow fit this shape without having any information that events are overlapping. That doesn't work. The good thing is, if we run it with overlap correction, well, I'm not sure. I think we are past considering linear duration, but the spline effect looks pretty good. And we look at this, well, we're currently looking at this with different noise levels, with different shapes. For instance, how am I doing with time? Yeah, I will skip a little bit over this, but we have different shapes, and then we get some kind of score, how well we are doing for different methods. And it turns out the spline typically wins. It's the most flexible one. Okay, I want to use the last remaining minutes to talk a little bit about Freeboard effects that we are currently looking at. And there's a cool data set called the ERP core data set, which I think they have 40 subjects, and they are all doing some controlled trials. So they're doing a P3 trial, like all classically studied EEG trials. So now you suddenly have data for all these trials in many subjects, and it's a really nice test bed because the data set is well described. It's publicly available in a nice format. The task we are looking at right now, we're currently also looking at others, is this typically oddball task. So in this case, you see letters A, B, C, D, or E, I think, and you're told in the beginning of the trial, whenever there's the letter B, press the one button. When there's any other letter, press the other button. Okay. And now, sorry, I don't have the slide, but now we have all this trouble, all these problems that I think this is very similar to the other paradigms that we looked at now. But what you typically look at, so you would typically time log your analysis to the stimulus onset here, and then look at whether the current trial was a distractor or a target or a distractor. This looks something like this. Yeah, so here is the stimulus onset, and then after like 300, 400 milliseconds, you get this big response, which is called a P3, where the target elicits a much more positive deflection than the distractor. Okay. So all that I'm talking about is still preliminary. I want to check this on another P3 data set, but yeah, it's been busy with lockdown and all the things. Yeah. Okay, so what we want to do is we know from the earlier slide that we have a reaction time effect. So you're faster to identify distractors, I think, than targets, or the other way around, I forgot. So we want to account for this. And the same thing that we did in the simulation. So now we assume we don't have a no overlap condition here because this is real data, but we could just analyze it typically as people would analyze it. Now we're looking at only one condition. I have the condition effect on the last slide. We could add a linear effect of reaction time. This looks like something like this. So yeah, people could do this and then they look at it and say, oh, wow, that's interesting. We have a linear response here over reaction time of this kind of data. Again, we know already from the simulation, this is probably not a good idea to do. And if you look at the spline effect, then you can also see that the spline effect, while here it's in it's similar regions and also similar regions here, it looks qualitatively, it looks quite different. Okay, but this is all. We already also know that there's probably an overlap effect of button press and stimulus onset. So this is without any overlap correction. And if you run this through overlap correction, it would look something like this. So maybe it looks a little bit different here. The linear effect is pretty much gone now, maybe in the baseline or so. I don't want to go too far here. And if you have the spline effect, it also looks different than what we had before here. And these earlier effects are a little bit gone. So basically what I'm showing here is, or this shows me that there seems to be some kind of consistent patterns of reaction time in our data time log to the stimulus event, right? So the stimulus response looks different whether I'm making a fast or a small reaction time subsequent to it. And I think people should take this into account. And maybe the most strong display is on this slide here. Summarizing all of this, we had this distractor versus target ERPs here. We have no overlap modeling, yes overlap modeling, no RT modeling, yes RT modeling, and we saw this. If I now do the overlap correction, I get something like this. So it's shifted a little bit. Maybe there are effects early or late. I don't want to. This is all preliminary data. I don't want to go in interpreting this too much. But if you control for RT, then this effect is pretty much gone here. And that was when I first saw it, I thought something's broken or so. But yeah, I mean, it can happen because we have the button press has a certain shape, and if you convolve this with varying reaction times or so, well, you can generate as large effects as here. But what I want to stress is this is not abolishing all of P300 research of the last 50 years or so. No, we're far from that. Because if you if you look at the button press response, for instance here, because we are modeling here stimulus and button press at the same time, then you would still have a difference in the button press between the two conditions. Just time lock to the button press. And there's also some ideas why this is the case in sense of evidence integration or so, which is you're integrating evidence for the two conditions, and as soon as you have enough evidence, you press the button, and then this evidence integration process should be time locked more to the button press than to your stimulus. Okay, but still, it's very interesting, and I think people should definitely look into this and understand better when this works, when this doesn't work, and whether this is a big problem or just maybe a small problem for such kind of RT-dependent experiments. And as I said, preliminary results. I didn't do any statistics, but I'd be surprised if this is not something that comes out. But yeah, okay, preliminary. And with this, I think I'm at the my allotted time, and I just want to highlight a few things. So the Unfold Toolbox, it works so far pretty well for me. You can use this cool syntax. We have lots of documentation and tutorials. There's open source code and unit tests on GitHub. There are 2 papers describing it, and we are currently planning lots of add-ons like mixed models and some Bayesian implementation. This is actually with Judith Schepers, who's an ex-Coxie and now a student co-worker in my lab. And so it's very exciting. We have implementation in MATLAB. This was the first implementation, works pretty well. And now we have, I really fell in love with the Julia programming language. And you're all very much invited to look at the toolbox, maybe try to implement something or just check it out. We are very open to contributors. And I'm always open to, if you like to spend some time working on this kind of methodological work, I'm very open to have thesis and all these kind of internships or whatever. We can just meet on GitHub. And with that, I'm very happy to take any questions that you have on any of these topics. Thanks.
Thanks, Wayne. So if people have questions, you can raise your virtual hand and we'll be open. So, Peter, please.
Yeah, thanks a lot for the great presentation, Bene. Really nice. I'm somewhat confused by your using whether it works or not. So I can understand, for example, if it's numerically unstable, then the model would not work because it does not converge to a solution. But I guess this is not the case what you are talking about. I could understand if the model is, so to say, inadequate, so that the variables are not suitable to fit the data. So the model converges on a solution, but the explained variance is poor, and in that sense, it does not work. So the numerics is all fine, but you don't arrive at a good model. The third case is everything is fine numerically, it converges to a solution, and it's about the interpretation. And here, of course, I think we have to differentiate the different problems of overlap and the typical artifacts, because the mass univariate data are not literally wrong. So if we go back to the N170 phase data, if you do a mass univariate analysis, the ERPs look as they are correct. Only your interpretation, well, looking at phases, you make shorter saccades, shorter fixations and all that stuff. And you want, like in a graphical model, freeze that variable and compare the data given constant fixation durations, constant saccadic amplitude, which they are not. The scientific question is valid to compare 2 different conditions at equalized nuisance variables. And insofar, at the end with the reaction time, my question is, on which level doesn't it work? Numerics, model, interpretation.
So I think numerical, we're totally fine. In some subject, we see that we have trouble, and we would some small regularization would be helpful. No, I forgot what the second level was, but I think that I would add a 4th level, and this is the level of assumption. Is the assumption valid? That this is similar to the interpretation, and I'm just so. This is very early for me to really believe that we are not doing something like that we're not misunderstanding something, that we have some assumption in our analysis that is just not a valid assumption to take. So and there's one candidate for that, which is sometimes called, I think, is it called post-stratification bias or so? That is when if you let's say you give a medicament and you check whether somebody gets healthy or not healthy, and then in this last bit you control for blood pressure, but blood pressure is actually the mechanism where the medicament works. Then you would find out that the medicament doesn't work if you control for blood pressure, right? These kind of things, and we don't have a good handle for that. And then does the like in the model specified, for instance, in this example, with this is something we're currently looking at. You could also put the nonlinear effect on the button press, time lock to the button press, and not time lock to the stimulus. And then what happens then? These kind of things. And it turns out that if you put them on both, then the model doesn't converge, because this is really little data. This is like 100 trials or something like this. Yeah, these are all questions. So that's why I'm still very careful to say whether and. Yeah, now I'm in the discussion phase, so maybe I can lean out a little bit more. But the like, just because our model might be wrong doesn't mean that it's the right thing to just do the ERP, right? I mean, this is the problems persist. I think we are clearly showing here that this model that these problems there's variability assigned to the reaction time. I think this is very clear that we are showing this, and I think people have to find ways to deal with that, because it will be. I don't see a way where this is not biasing. No.
Okay, nice. Thank you. Thanks a lot.
Okay, so we have a question from the live stream. So there was a question regarding plans for porting this to M&E and Python. And so Python is more and more popular with EEG analysis these days. So would you think it's a worthwhile task to do that?
No, absolutely. So I'm not going to port this to Python, let's say it like this, but the nice bit is Julia is really easily callable from Python. And we're actually right now, we're writing on an interface where you can use just use your M&E data and just run it through the Julia toolbox. And yeah, you still need to manually install Julia, but that's about it. And then you can just run the model in Python. That's a big benefit of going to Julia. Besides, it's a cool language, and it's faster, and it has, yeah, I really like it. But yeah, it's definitely, we're also working with Philip Alday, who was used to be an M&E, not collaborator, but, you know, a contributor. And he wrote also a Julia toolbox where you can call M&E in Julia, so which is also super nice, because then I can stay in Julia and I don't need to run Python. Yeah, so it's a very good point. We also are planning to do an R wrapper in case you want to call the EEG analysis from R, just because it's easy with Julia. Cool question, thanks. Yeah.
So I have a question of my own as well. So when I think I've asked this question before when you've presented this. So you talked about continuous EEG data, but like analyzing this. But what if we want to do this modeling at the trial basis? Is it still possible to do that? And what are the pitfalls of doing this at the trial basis?
Yeah. This is a question we get more often than not. And the reason is that most EEG analysis so far, like cleaning of trials or so, has been done on the trial level. So the epoch data is already there. But that's a problem for our case, because you don't know what happened in the past, right? You can have a single trial, but then you don't know where is this trial, did this trial come from? And if you have trials that are very close in time, or you make very long trials, then you might have multiple data, the same data in several trials. So there are some cases where you can do it in sense of if you just have like the speed 300 and you have long enough trials that all the response and the trial is in there, and you don't have an overlap to the next trial or something like this, then you could like concatenate your epoch data again and get a fake continuous data, and then analyze the EEG. And there's some code in the MATLAB toolbox. It's in some development branch. Yeah, but the problem really is that in one trial you don't know what's the overlap of the events that were before this trial, because they are cut off. It really depends then if you can do it or not. Most likely it's easier to just use the continuous data.
Mm-hmm. So we are open for more questions also. I would urge the participants to ask more. We usually try to extract as much information from the speaker as possible. And until someone asks another question, I have sort of a confusion regarding regularizing these betas. So you didn't talk too much about the regularization, but you mentioned it. So does this just, you can use a simple L2 regularization and that's it? Or do you need something more fancy to do this?
So the simple answer is yes, you can just use simple L2 regularization. So you punish for having large deflections. The problem is, I mean, the conceptual problem is, or what problem? If you have normal ERPs, I showed you that this are also just linear models, right? So you could also use regularization in normal ERPs, but nobody does it. There's a single paper, I think, that use regularization that I'm aware of right now. There probably be more that I'm not aware of. That looks at ERPs with regularization, and I think this is partially a reason is historical, or that we just don't really know. We want to report what is really observed and not what it just gives you a good prediction of the held out data. That's, and I come from a statistic, like there are like multiple ways of doing statistics, and I come more from the likelihoods kind of inspired things where you wouldn't do out of sample predictions or out of sample cross-validation things. But if a machine learner would see this problem, he would definitely use just regularization by default. And for me, regularization is a special thing. Yeah, this is definitely something to look in. It's on the list of many things, many problems. Yeah, I'd be also interested to hear more opinions on that bit. Yeah.
So what effect do we can we expect when we do regularization? So the curves would be a lot more. So I'm not really well versed with what happens when you regularize a time series, for example. So I'm not sure what advantage we would have when we do this at all.
Well, you would have like, so the regularization would, if you have noisy data, so it would scale down all the betas, and it would trade off, it would introduce some bias, because now the betas is not the true effect anymore, because it's close, it's biased towards zero, but you have less variability in the betas. So in our Unfold paper, we actually have a nice plot, which I don't have here on the slides, where you show where we show then yeah, basically in the unregularized way, you're much closer to this original shape that you try to approximate, but it's super noisy, and then you trade off noise, and but everything is like squeezed down to zero. And I think that what exactly the regularization does depends also, of course, on the shape, because it punishes large values more than small values and the like. So yeah, and I don't have enough experience to be honest in when to use regularization and what to expect.
Mm-hmm. Thank you for that. So we have a question from Peter again. Please, Peter.
Yeah, a comment to the regularization issue. The approach of regularization, but if you use L2, it tends to press variance into many small parameters. So if you choose the size of the kernels to be fitted, because you don't know the degree of overlap or the length of the ERPs, you typically choose a liberal size, so with very large kernels. If you then allow L2 regularization, you will have non-zero entries in many of these distant coefficients. And so my gut feeling is I would prefer L1 regularization. I want to have those few large values which really are relevant, and that everything which is far away, close to zero, actually to zero, because most probably these are spurious statistical effects. So regularization, yes, but whether L2 regularization is a method of choice, I'm not too sure.
You're a little bit in luck, because we also implemented L1 in the MATLAB toolbox, and actually we use GLMNet, so you can choose between L1 and L2.
I love Unfold. It's okay.
And the second problem you mentioned is that you want to have long events or so. That's a nice bit in Julia. You can actually, for each event, you can define how long your basis function should be. So maybe you think button responses should be more backwards in time, and stimulus answers more forward in time, so you can adjust that. that's a nice thing. If you implement the toolbox multiple times, you can do it better and better every time you implement it. Yeah, no, it's a very valid thing, and I don't know. The problem with L1 is that you might get very spiky ERPs. I've seen that in very noisy data set. That where then often it was just 0 because that was what L1 does, and then you get these spikes, and it's just very non-natural looking if you're used to ERPs. But it doesn't mean it's wrong, right? I mean, what is right, what is wrong depends really on how you look at it, I guess.
So just a comment to that, L1 is usually used as a feature selection. So you could extract time points that are most important for these differences to occur. So that's essentially what's happening there. But it's also nice to if you use L1, then you could use unfold plus L1 regularization to actually figure out like some feature selection, for your EEG analysis also. That's actually quite great.
Yeah, maybe. I recommend simulating first. No, that would be a cool project. Yeah, somebody should come to me and work on that, or just work wherever they are on it. I'd be happy to help.
Okay, so we have another question from Rosa. Please go on.
Yeah, thank you for your talk. It was really interesting. It sounds like a really useful method. I have a question on the upward paradigm you presented lastly. Is it possible that there's also such an overlap effect if it's a passive upward paradigm? So if there's no action required, like if you're not really measuring reaction time, but it could also be that there's a difference in reaction between the deviant stimulus and the standard stimulus?
Yeah, I think this is a really, really good question. So just to rephrase it, that I got it wrong. What happens if I just don't ask people to button press?
Yes.
Yeah, and you still see the P300. And then obviously I don't know what's happening in the brain because I don't have this event to take it out, right?
Yeah.
I think the same thing happens actually. There's even if you're distracted, I think you would have you see some small type of P300, but we are just lacking the way to look at it. There are tools like the right toolbox or so that tries to infer like unknown components or so, and tries to get rid of this. My gut feeling is that you would also have the same effect, but you can just not analyze the data.
Okay, so we just cannot use the unfold method to rule it out.
Not yet. Maybe at some point you can, but right now, no. You need to know when the events are. Yes.
Okay.
Yeah.
Thank you.
Okay, thanks, Rosa. More questions?
Just ask me about Julia.
Okay, so I see on your slide that the mixed models is in plan. So when you have the random effects from so what you show, the betas that you show are basically fixed effects. When you have random effects, what would that tell us? So would you get these betas for each subject, and then you have separate like ERPs per subject, or what would the random effects actually tell us?
So actually, it's already in place. So in principle, it works in Julia, but the overlap correction is really it's huge models, and so we're still working on it. But you can also use mixed models just for normal ERPs, and maybe it's easier to think about that. And then you just like I would typically look at what's the variability, or like what's the variance of the random effect over subjects. So that gives you a measure of how variable are subjects over different time points. And the nice bit is then you can also control for item effects, like if you have different, because you want to not only make a statistical Aussagen, well, I'm missing the word, statistical statements about this set of items. Maybe you have 15 natural scenes or 15 faces or so, but you would like to generalize to all natural scenes and all faces. And mixed models would, in principle, allow you to do that, which I think is very important to generalize your and take sources of variability into account. But yeah, the mixed model part, I mean, it's developing. We are just starting out collaborations there, also with people who look at cluster permutation tests. So how would you even start to do statistics with these mixed models? And yeah, there's a lot to be explored. I think a lot to do. Yeah.
Thanks for that. Okay, more questions. Peter, please.
Yeah, if there's time, I have one more question. Often with model selection, explained variance is taken as a criteria to select the best model. Now the EEG data are typically noisy and explain only a small part of the variance. What would you recommend to determine the level of complexity of a model?
I recommend that people write lots of simulation and have a look at it. I don't know. What we currently were looking at is simple R-squared. It turns out that if you have the spline predictors, R-squared is typically also cross-validated. R-squared is can be pretty high. So in I think in the scene viewing or so, we find R-squared of 0.3 or so, a 30% variance explained, which I think is pretty reasonable. But I think there are fundamental limitations in some sense of this method to get even higher R-squared, and that's because we have things like alpha oscillations or so that will more or less can also happen at random non-time locked ways. So yeah, right now I think I would just use R-squared, but I think AIC is also implemented, but they are all similar in some sense. I don't think there's a super good answer to that right now. No.
Okay, thanks.
But I mean, in normal ERP research, also nobody really looks at that. So maybe we are a little bit more on the safer side here.
I think it should be looked more at.
I totally agree. Yes. But it's hard. It's not straightforward. There's a lot of pieces still missing, or of things that we can now only look at. Because we have enough powers, computational power, and enough understanding of the statistics, I think. Yeah.
More questions? So I think I have, I'm sorry if I'm asking too many questions. So this looks deceptively similar to encoding models that people use for modeling the response function of neurons. So if you have a moving stimulus of like alternating lights or something, then you can figure out what the response function of the of one neuron is. Is this so? What sort of statements can you make from these betas then? Is it just the response function for faces versus cars or anything else? Or are there granular statements to be made here? Because you have the response of the whole brain here, you know, and then you have responses per channels as well. So is there a larger statement to be made that it's not just the response function for face or not, but something else?
Just a response function. So cool. No, but it's just a response function. Yes, this is all. I would call them, maybe I'm wrong, but in my lectures, I call them encoding models for exactly that reason. So you're trying to predict the EEG activity, and for that, based on some features, and for that, it's an encoding model. Totally. And you can also, like the people who went from this, they used this temporal response function, this continuous, like this continuous features that were as long as the EEG, right? They come from a filtering background in some sense, audio filters and likes, and they call the temporal response function, which is just the filter response of the brain. So what happens if I change this a little bit? And in order to measure a filter response of just a signal filter, you can just use a white noise signal or so, and then just see what comes out, or just a spike, which would be an event, or showing a stimulus for a short time or so. Then you can think of the ERP as being the filter response, right, over time. Yeah, if it's just a filter response, I don't know. Obviously, at some point we have to move away from static analyses of these kind of things, but I think we're not there yet. And so far, it has been a very, very productive thing to look at these ERPs, I think. But yeah, think of it as filter responses if you like. Maybe it puts it in the right window. Maybe it's useful to think of ERPs just as reaction times, or like because sometimes you're over-interpreting what you can. I'm over-interpreting how much you can say from an ERP or learn from it, maybe.
Mm-hmm. I'm trying to think of a counterpoint, but I can't right now. More questions. We still have a couple of minutes left. Okay, so since we have no more questions, I would like to thank you again for a great talk and a nice discussion.
Cool. Yeah, thanks a lot for having me, and yeah, thanks a lot for featuring also methods work. It's not always the most popular ones, I think, but I think it's super important and it's a lot of fun. So I encourage all the Coxie students to just yeah, work on these problems. They can be fundamental. Things can be found out just by doing these things. Cool. Thanks a lot for having me, Ashima. Thanks for the invitation, and it was super nice to be virtually back in Osnabrück and yeah, talk to student Coxies again. And so it's very cool. I missed that. Yeah.
The pleasure was all ours. Thank you again. And to all the participants, the YouTube video will be available on the channel, and hopefully more students are interested in this after watching it.
Cool.
Thank you again.
If you have any questions, just contact me, right?
Cool. Okay, thank you.